Welcome to today's lecture on design analysis of orbit motor 2, which is geometric volume displacement. In earlier lecture, in part 1, I have discussed about the geometric design of the star and envelope, that is ring of an orbit motor. In this lecture, I shall show how to estimate the geometric volume of a chamber and then swept volume, and how to find out the volume displacement rate with the shaft rotation. So, as discussed earlier, the epitachoid generated ropimas, that is rotary piston machines, orbit and gyratory units, the envelope ring forms the chambers, whereas the epitachoid star acts as a piston. If we look into this, so this is the chamber. So, one particular chamber is shown here, which is formed by, we can say that the outer member, that is an envelope, that is ring, is the cylinder, and this is acting as a piston. Unlike the cylindrical piston machines, in this case the area varies, and so variation of volume with the shaft rotation is equal to the variation of area multiplied by the thickness of the star and ring, which is constant. It is also discussed the number of chambers is equal to the number of chronodes of the envelope, that is equal to Z. So, the number of chamber will be equal to the number of roller in this case, or it might be sometimes integral part of the envelope, whereas we know the lobe of the star will be 1 less than this. So, here there will be 6 lobes if we take Z is equal to 7. Again, in earlier discussion, what we have seen that the ripple is less in case of odd number of chambers. So, while we shall discuss or the formulations, particularly we have to be careful, formulations are like that Z is always an odd number. That means, number of chambers are always odd. A complete cycle of piston action comprises of 2 phases, namely volume expansion and volume compressions. Let us look into this. So, this is the star and this is the ring. This is modified epitachoid, what we have learned, and this is basically envelope, and this modification is nothing but the constant difference inward shift of the original epitachoid generated. So, for which the envelope actually goes through this center point envelope, and then if we modify this envelope, what we find, this contact portion becomes circular arc. If you notice this rotation, you will find that this contact is not up to the full arc, it is some angle, the maximum leaning angle you can say in both directions from the center. So, but the thing is that we can replace this, we can either make it integral or we can replace this integral part by roller. Okay. Advantage of roller I have already discussed, which is that we can replace this roller if this is worn out. Okay. Now, other part of the envelope is that this circle on which these rollers are kept, I mean on the outer body, this is slightly less than the circle, the which is called pitch circle, slightly less than that. So, this roller does not come out, and it is selected on the basis of at the topmost position of this roller. Okay. Now, this we can call that at this position the piston at its top dead center, Okay. Now, when it will rotate, you will find gradually this space is being increased, the black space is being increased, that is the change in area. So, if we can estimate that change in area, then if we multiply with the thickness of the star and this envelope, which is equal, nominally which is equal, we can estimate the volume displacement, and that is that we will learn today. But one important thing here I would like to discuss, that if we consider this is the bottom dead center, then at this position you will not find any other chambers in top dead center. Top dead center will be, which one will be the top dead center in next, while it will start rotating, you will find that this this one will become the, it will reach at top dead center, this one, just a small rotation. Let us see, you can see this, it is already at bottom dead center, and then again say suppose this is the minimum, at this position you will find after a slight rotation this is becoming at top dead center. This angle can easily be calculated from the phases of such orbit motor, from the analysis of the phases of such orbit motor. It is important to examine for the flow distributor valve action. If we analyze the flow distributor valve action, the duration of those phases in terms of shaft rotation for a single cylinder as well as the multi cylinder action. So, what we have to do, we need to analyze how long a chambers, or what with respect to the shaft rotation, at what angle this bottom dead center and top dead center is occurring, and according to that we have to also look into this and the distributor valve, they should act accordingly. So, this phase analysis is not shown, it will not be shown in today's lecture, but we will accept that when this is in expansion mode, then one the oil in channels are connected, and when it is in the compression mode, the oil out channels will be connected. Okay. Now, in the analysis, the initial position of the output shaft, that is the shaft rotational angle theta, is taken as 0. What we are considering with this axis, when this crest is at top dead center, that angle is 0. The center C and O lie on the x dot axis, this is x dash, and here is the x. So, it is lying on this axis, both this axis of the star as well as the axis of x axis of the envelope, they coincides, whereas y axis is away at the center distance C O, whereas this one is the, this is on y axis through the center of the envelope, and it is one of its dead zone, we have called it the top dead center, and this is in the threshold of expansion phase. That means, immediately after that, if we rotate in the clockwise directions, here the expansion mode will start. Okay. Now, This means that the centers are interchanged from their original initial position during generation. So, in the previous lecture I have explained that how this generation is done. In that generation technique, what we took initially, that the center of the star was here, or the centrode fixed for star was here, and the center of the star the ring gear or envelope was here. Whereas, when we have started operations, we have just interchanged the center. This means that while we shall consider the geometry for the envelope, we have to take care of these transformations. Okay. Now, the positive z axis is along this z, do not confuse, this z is not the number of the lobes, but this is the z axis, x axis, y axis and z axis is in the upward perpendicular direction of the plane of the paper, that is in this, it is from the here will be the z axis, which is coinciding with the axis of the output shaft. The output shaft is also directed outward. So, z axis is coinciding with that which I have just told you. Now, we have taken some axis on the star and ring. What are those? We have taken a C S1, C S2, C S Z be the central axis of the cylinders. This means, on the envelope, we are calling that envelope is acting as a cylinder. So, on the envelope, from C, the center of the envelope, to the center of this portion, that is, you can say the center of the chambers, that we have designated as C S. Now, according to the number of chambers, we have numbered the chambers also. We have given the S1, S2, S3 etc. Now, here I have mentioned as a jth chamber, any jth chamber, but on the with respect to the figure which I have drawn, we should say this is chamber 1, this is chamber 1. In the phase analysis, I have shown that this is the chamber 1, next chamber is chamber 2, whereas the chamber on the x axis, along the x axis, when the rotation is 0, in that case this chamber is chamber 7. So, this is, you say, if you put this number, this is H 7, this is S 1 and C is the center. Okay. Similarly, we have taken O T 1, O T 2, capital T, O T Z minus 1 be the central axis through the crest of the convex portion of the epitrochoidal lobes. So, this is the convex portion. If we take the topmost point, the crest point, then we number is O T 1, O T 2 etc. But if you look into this case, we have taken as if the O T 1 is here. It can be named otherwise, this is the T into Z minus 1, because there will be 6 lobes, one lobe less than Z. So, that is why number will up to the Z minus 1. Similarly, we have also taken O small t 1, O small t 2, O t 2, that is through the lowest point of this profile. Okay, that is the concave portions. We have taken this. Now, these lines, while we are analyzing the phases, then which one is coinciding with which one, depending on that we are giving the number we are assigning. This is easy to understand, but in the present analysis, our main concern is to estimate this area at any instant. We will find this area, and you may find that these are not much useful here, but while you are writing something, presenting something, you can say suppose O S 1 has coincided with O T1, capital T1 or O capital T2 like this. That is easy to understand. To estimate full active volume of a chamber, the volumes at top dead center and bottom dead center are calculated. Suppose if we would like to find out what will be the volume expansion of a chamber, we calculate the volume at top dead center and bottom dead center. Top dead center means when the piston is at the top, that means this is the top dead center. Whatever the volume at that condition, that is not the active volume, that is not the varying, that is a constant volume that will be always there. So, we have to calculate separately this volume as well as we have to calculate when is the maximum volume at bottom dead center, and then if we subtract this we will get the volume of a chamber. When the shaft rotational angle is equal to 0, OT1 coincides with CSZ. In that case CS7, if we take this Z is equal to 7 and chamber Z is at its top dead center. Okay. Now, after an angle that is eta 0 which is calculated as pi by Z into Z minus 1, we will arrive and another chamber which is given by Z minus Z plus 1 by 2th chamber reaches at its bottom dead center. But I have doubt, I think this will be minus. This will be true if we consider this is chamber 1, but we have considered this is chamber 1. So, possibly this will be Z minus 1. So, that we can examine. Let us see again. Say if we let us consider this is 1, no, this is 7th. So, 1, 2, 3. So, third one is reaching there. So, this will be Z minus 1 by 2, not the Z plus 1, it will be Z minus 1. But this angle, say this was at its top dead center when the shaft rotational angle was 0, whereas this will be at its bottom dead center, then the shaft rotation can be calculated as pi divided by number of lobes on the envelope into the number of lobes on the epitochoid, that is star, the ring number. So, suppose in this case we have taken 7 and this is 6. So, pi divided by 42, it is around 4.3 degree or 4.27 degree, for after which this angle will be this chamber will be at its bottom dead center, that is the maximum volume. So, what we can do, we put the shaft rotation angle 0, we consider this 7th chamber, we calculate the volume, and next moment after 4 degree of rotation we consider the chamber 3 and we calculate the volume. Then this volume minus this volume will give the volume of the one chamber, one maximum volume displaced of a chambers. Okay. So, this we have to do, but we must calculate this area now. So, this what I have discussed, this is told here. Now, next slides what we will see that referring to this figure, the area AJ means area of the jth chamber at an instant when this has rotated by any angle. It is bounded by this area bounded by GHBD. Now, it is necessary to express the chamber area with respect to the axis fixed on the envelope. We will find out this area considering this axis, the fixed axis fixed to the envelope or the ring. So, the axis x c x dash and y c y dash fixed on the envelope are also axis of the fixed reference frame. That means, this is fixed. So, this you can say the axis of the fixed reference. So, we will transform all coordinates with respect to this to estimate this area. Assuming the simplest modified form of the envelope, what does it mean? We have assumed this envelope is nothing but that there is a circular ring and this is on a ring with the inner circle of this one. So, this is the simplest form which we have considered, and the instantaneous area A j of jth chamber is given by A j is equal to A 1 minus A 2, where A 1 is the area bounded by the curve joining the points C, D, G, H, B, C. So, we shall calculate C, D, G, H, B and again C. This area we shall calculate minus the area bounded by the lines and epitrochoidal curve joining B, C, D. So, if we subtract now this area from this area, we will get this instantaneous area of this. Now, how it is done? So, geometrical, this is pure geometric analysis. Referring to this figure, what we find, this is the area indicating C, D, G, H, B, C is equal to area C, E, G, H, then F, then C. First we consider this area. Okay. So, this is like that, we are considering this area. Okay. Now, next we subtract C, E, G, D, C. Now, we subtract this area and then we add C, F, B, C, this area, and then finally, we subtract H, F, B, H, H, F, B, H, that area we exclude. So, ultimately, we are getting this area. So, this you can check yourself these equations, and you will find that we are calculating ultimately this area. Okay. Now, area in right hand side can be expressed as follows. This is purely geometric analysis. First, we have considered this one. This is, we have taken pi r s, where r s is the radius of this inner circle. Pi r s square by z, that is the whole area, minus r a square. This is, we have taken 1/7 of this area, because this area will be 1/7, and then we have taken r a square arc cos. You can just understand this, how it is. This is the cos inverse, arc cos means cos inverse of this angle. So, this will give one pocket, and then next we shall consider the another pocket, we will get this one. So, this you just you have to take this figure, and this you have to understand. Here a 0 square is this is the a 0, this is square, then r s square we have taken this square, minus r m square is this one, cos inverse of that into R A square will give you this area. Okay. Now, plus R m into A 0, R m into A 0 into 1 minus this will give this area. So, we are going to get this area out of that. Next, we consider the area C E G D C, C E D G and again C E D G and C. That means we are getting this area. This is again, if you can find out that first this is a triangle we have considered A 0 into this is perhaps not R 0, it will be R m, vector R m, this will be R m. So, this is slide number 7. This is R m, that means we are getting this perpendicular, A 0 is this one. So, we are getting the area of this triangle, this one, then plus half R m square into cos inverse of this angle, that we are getting perhaps this area, okay, this area, we are getting this area minus minus this area. Oh, okay, we are getting this area and then minus this. So, we are ultimately getting this area here. Now, next we will consider CFBC. So, CFBC, this is simply half into A 0 R m by sin phi j. These angles are called leaning angle that can be calculated for rotation of this shaft, which I have discussed in the last lecture. And finally, HFBH is nothing but this angle. So, this area, this is R m square into cos of that plus half R m into phi j. That means, we have considered this area first and then we have considered this area. So, now we are we will substitute this value in equations 832 and in non-dimensionaling. Now, here is the question of non-dimensionalization, which I have shown in earlier case. What we find that area any distance, we have put a bar. The bar means it is the non-dimensional value, non-dimensional parameters. So, in that case, what is done, each and every parameter, say if it is a length, that it divided by R 0. What is capital R 0? What is capital R 0? Capital R 0 is the radius of the centroid, the bigger centroid, the centroid for the envelope. So, we have divided by R 0 to make non-dimensional of any length A 0, R m, etc. So, this means that while we are considering area, suppose we have calculated this one, what will be the actual area? Then A 1 bar into R 0 square, capital R 0 square will be the area, that you should remember. Now, in the non-dimensional form, this can be expressed as that. I am not reading it. So, this when this equation is available, you can just sum up and non-dimensionally you will arrive into that. So, now we have calculated only one area A 1. In the next page, what we do, we find out how the A 2. Now, for this A 2, the coordinates of B and D with respect to x or y, where this angle is with the reference to the original generation of profile epitrochoids. You just look at this. This angle indicates the shaft rotation, whereas this angle with respect to the original development of the profile. Now, what you can find, say this angle for the generations we take for the jth chamber, psi j is equal to beta. Beta is in this case pi by z. That means half of this angular spread between two rollers plus the angle of rotation. Okay. So, beta plus angle of rotation we will consider for this one. Similarly, for the other one, this angle we will consider beta plus 2 pi by z plus this angle, the shaft rotations. So, in the original formula of the profile, we will put this value and this value to get the coordinates of these two contact points. Okay. So, therefore, these coordinates can simply be written in this form. If you use this one, you will find these coordinates. Okay. So, this is being transformed from the original coordinates what we have calculated with respect to the reference frame. Okay. First of all, we have to calculate these two and then we will transform in this coordinate system. Next, here I have mentioned this beta may be pi by z or any other angle, only we have to take care of the proper geometry. Now, next we will express the A2 in the dimensional non-dimensional form. Now, this is from this epitrochoidal geometry, it can be shown that this integration will give us this area A2. If we would like to find out this area, then knowing these coordinates of these two, we can differentiate like this. Now, here I have presented this formula, this is from the earlier lecture. So, this is the formula for expressing the coordinates of the envelope at any this psi angle. Okay. Now, in that case we have calculated these angles separately and we are adding to that. Remember, we have to calculate leaning angle while we are trying to calculate these coordinates of any contact point. That is, you have to also take the formula in the earlier lecture to calculate this properly. Okay. Now, if we evaluate this integral, we will arrive into this formula, but still one integration part will be there for which this can be expressed in this form. That now, this integration is not presented in the any closed form solution is not given here. So, we have to go for numerical integration to evaluate this. Okay. But maybe a mathematician can find out something, but otherwise we have to go for this numerical integration. And this is that you can find out this also. This is not difficult to find out. This is the leaning angle, that means this angle. So, finally, okay, before going into calculation these chambers, here one interesting note is given that now we have calculated in the as a A2 this area. Now, at any instant, if we add all such areas together, that must give the area of the rotor, which is important to find out out the envelope, I mean total area under the profile of the star, which can be simply if we add all the area calculated like this at any instant, we can simply get this area of the star. Okay. Now, the second term in is nothing but the area bounded by d O B. This equation can be modified to the form this one reference, you will find that one reference he developed the formula in other way. It was to me it was more cumbersome, but I have simplified this formula and we arrived into in this form, which we will see in the next slide. Okay. So, what I have done, I have substituted all the findings, all the formulation in non-dimensional form, and ultimately we get this will be the area of a chamber at any instant. That means, when the shaft is rotated by this angle, okay, we will get this angle, or so to say I would consider, if we consider any j and whether it is rotation is 0, 1 degree, whatever it might be, if we substitute these values, we will get this area of a particular chamber. If we consider the next chamber, we have to take all such values accordingly. The rate of change of this area with respect to the output shaft rotation is expressed in general form for both inward and outward modifications as follows. Now, what we have done, we have first calculated this area. Now, here we have derived this as a rate of change of this area with respect to the shaft rotation, which now becomes in this form. If we look into this, this is basically, you will find that this motion of this epitrochoidal area, this has no connection of the other geometric relations. It is obvious, the fixed part is eliminated in this case. It clearly indicates that whatever shape we take for this envelope, keeping this active envelope portion intact. That means, instead of taking this portion and this fixed portion as this circular arc, even if we take a big hole or even if we make a curve like this equation will remain same. So, because this is only the variation of the volume, which is working volume. Now, if we get this one, then here I would like to mention one thing, that this modification may be inward and outward. This profile can be modified outward also. See, in case of Wankel engine, this is modified in the outward directions, like that, a small modification of course. So, to accommodate this, whatever may be the modifications, in that case of obviously it is inward directions. What we have done, we have used a equation cos phi 0. In fact, this phi 0 we can put along this axis. So, when this angle is pi, that means this becomes minus 1, this is for outer modification. That means, in this formula for the orbit motor what we have considered, we will put minus 1. So, this will become plus. Okay. Whereas, if we modify in the outward directions, we will put this is equal to 1. That means, in that case this angle is 0 and in inward modification this phi 0 angle is pi. So, it is coming minus 1, that we have to remember. Now, again, so this variation, this is obviously will valid for whether in compression mode and whether it is expansion mode. Okay. But we have to identify very carefully, as long as this is in say expansion mode, we will add with the other chambers which is in expansion mode, because these machines in orbit machines is also a DC machines, not alternating machines. All the flow is being mixed. Suppose at an instant we find the chamber 1, chamber 2 and chamber 3, this is in the positive value. So, we will put this DAP, that is in expansion mode, and whenever we will get, say for the chambers we will get this is minus, we will put that separately and we will make that this is in the compression mode. But interestingly we will find that summation of these positive and negative will always constant. That means flow in, flow out will remain constant. And another interesting information I would like to give you here, although it is not shown, but if you take one chamber to the corresponding chambers, you may find that the volume in and volume out is not same, or in other words, when say one chamber is in the expansion mode, let us consider in this case, or if I consider the fixed axis, in that case this angle will be nothing but this 2 pi by z, that is the angle for any phase is expansion and compressions. Now, this phase what we find 1, 2, 3, 4, 5, 6, 7 degree, this has we will make it. Interestingly we will find that for a particular angle the compression and expansion of a chamber is not equal, whereas in case of ordinary piston machines this is equal. So, whatever may be the rotations, whether it is suction or compressions, you will find a single degree of rotations, this volume is constant. In this case, these volumes are neither constant nor it is matching with the expansion phase and compression phase. Whereas, if we consider the overall, that is matching and it has to match, otherwise this machine will become impossible, it will not rotate smoothly. Anyway, our purpose is to find out the swept volume. So, it is to be noted that this rate of change of area is independent of the shape of the inactive envelope. This is inactive envelope. Maybe say suppose this is the contact point up to this. So, this portion is active and this circular arc and this circular arc all inactive. So, it really this formula is independent of this area, whatever it might be. Sorry, whatever the area in equation 9, which is different for other approximated curves, is only useful to calculate the area and volume at an instant. Only thing, suppose if you would like to find out the trapped volume, unused trapped volume, then you have to consider the geometry. The expression of for flow rate, speed, ripples, etc., for such rotary piston machines with different kinematics, that is zerotor, orbit units with star output, ring output, etc., can easily be derived with the help of equivalent system concept. What it is? Now, orbit motor, what we have seen, the ring remains fixed and output is taken through the star. Star is having two rotations. One rotation is the revolving actions around the central axis, that is the axis of the outer ring, and it has also rotation about its own axis, which is the output in case of orbit motor. And orbit, this version is only used as a motor, because other pump version is not efficient, not beneficial from the transmission point of view, volume displacement point of view. It needs, if we make and pump with orbit principle, it will need large torque for slow speed, which is not available from the engine. So, it is not beneficial. On the other hand, when we make it fixed axis, then which is called G rotor, also a special name is assigned G roller when we use this type of roller. When it is integral, usually call it is G rotor, or we should call in general case it is G rotor unit, that is fixed axis unit. What is fixed axis unit? In that case, both rotates about their own axis, but even they rotates about their own axis, you will find this compression expansion, that variation of this area will occur. So, that can be used as a pump as well as that can be used as a motor also. Now, what we have done, we are analyzing all such area and everything with respect to the orbit motor, but it is possible that if we know the kinematics, so same formula also can be used for the other kinematics, that means G rotor units. How? Let us see. Now, what we do, the general flow we can express that what we have derived, that this is 2 pi n r, n r is the output rotations, the b is the width. So, d a p and d gamma, this gamma is general angle of rotations we have given. So, this simply if you add them, you will find out what is the rotations, and in case of orbit motor, this we will put eta, and this is the output rotation of the shaft. Now, this angle is nothing but transmission ratio into this angle. This transmission ratio we have derived separately, which is not given here. So, directly if you would like to use this formula, you had to know this transmission ratio in terms of the gearing in between this star and ring, which is tabulated form available in one of the references. Okay. Now, in case of obviously in case of orbit motor, we will put this as a 1, orbit motor this as a 1. So, we can easily calculate this one, or simply this will be replaced by this 1 in case of orbit motor. Now, here I have written is in case of 1 for orbit unit. So, without following the table, you can still calculate this if you follow this one. For G rotor with unit with ring rotation, when the ring is rotating, simply you put 1 by z minus 1. So, we will get this value, and then this flow rate will be for that G rotor unit with ring rotations. For the star rotations, this will be 1 by z, and we will find this the same expression. In case of orbit motor, this is 1. However, the generalized dimensionless swept volume V s can be expressed for unit width, width is given by B of star ring as follows. What we do in case of, so this first we calculate this I t is 1 for say orbit motor, and then we multiply with this. This is flow rate volume in, and we integrate up to this angle, and then we simply find out. So, this is, I would say rather it is a complicated form to find out the swept volume, but automatically from the flow rate we should be able to get the swept volume. So, this is shown here, but I will show you the simplest way of calculating the swept volume. Now, this is again the same thing I have described here while you are using this formula. the average geometric volume displacement Q A average, you see this, if you estimate this one with respect to this, there we will find the flow fluctuation. So, what we should do, I mean once we calculate this, we simply multiply with the width factor, and because this is for the unit volume, unit width. So, we have to multiply here with B and then the rotational speed. Now, the alternative method of calculating swept volume, this is just to calculate the swept volume. What we can do? We can calculate the BDC and TDC at area of the chambers at BDC and TDC, and which I have earlier explained that if you, for the geometry we have considered, if you consider this angle is equal to 0, then you can first calculate this area at chamber 7, which is the chamber at top dead center, and then after a rotation of pi by z into z minus 1 angle, you can take the other one, that is z minus 1 by 2, that is in this case this will be third chamber after this, after that rotation of pi by z into z minus 1, and then you will get the bottom dead center area. So, and then what you would do, the working volume is nothing but the area difference of these two areas into the width. Now, the swept volume is calculated then as follows. For orbit motor, what we do, simply this volume of one chamber into this action in one revolution. That means, how many such chamber actions will be there in case of orbit motor? Z into z minus 1 time. So, you simply multiply this, you will get the swept volume of orbit motor. Interestingly, in orbit motor, this is one respect to the other. That means, either star rotating with respect to the ring or ring rotating with respect to the star. So, in that case, there will be single formula to find out this swept volume, whether the star is rotating or ring is rotating. Whereas, in case of zerotor unit, this will be either V c into z or V c into z minus 1, depending on ring and star rotation respectively, because in that case, suppose your star is output, both are rotating, star is output. In that case, you will find that when the star one full rotation is done, actually 6 chambers are displacement is there, not the 7 chambers. Whereas, if the ring is rotating, then 7, I have mentioned 7 or 6, in that case z minus 1 and z. So, carefully if we use, we can calculate the swept volume of the ring, I mean zerotor, depending on which one is the output. Let the star ring of an orbit motor have the following data. We will take an numerical example. Now, in that case, we have taken z is equal to 7, E 0 bar is 1.625, R m bar is equal to 0.405, beta B is approximately 0.7, it is slightly not 0.7, some value is there, and R s means this one is 1.55, whereas R 0 is 19.6805, approximately 20. So, you can imagine what is the actual dimensions. Okay. Then this is R 0 is the radius of the inner centroid for the epitrochoid, which is 16.869, but this is not required because we have non-dimensionalized with respect to this one. Interestingly, say we use A0 Rm bar, but we never use this C0 bar, because C0 bar is nothing but 1 by Z, because this you will find this and a relation R0 by capital R0 by small r0 is nothing but Z by Z minus 1. So, at their difference will be 1 Z. So, this means that C0 bar is 1 by Z. So, in the formula you will find that not C0 bar is used, only 1 by Z is used. Okay. So, with this data, if we calculate this area, what we have done for the swept volume AZ, we have taken first A7 we have calculated, and then this is again I have made a mistake. This will be minus 1 by 2 the third chambers, and this is A3, and we will get this now this area. These two areas are A TDC and A BDC respectively. Therefore, we will now use equation 14 to calculate the working full volume of a chamber, which becomes this, and you see this I have not shown the calculation, but to calculate this area we have used this formula, and ultimately we have found out that this full volume of a chamber working volume will be around 2 cc, very close to that. So, therefore, the swept volume of an orbit motor of with these data, it will be 84 cc per revolution. The flow required is 84 cc. So, you can imagine that in case of the fixed axis, it will be either 7 times less or 6 times less than that for one revolutions. This is one. Second thing, look at the size. Size is say A0 is 1.625. If you multiply with this 20, it will become 20 plus 12, 30 or maybe 35 millimeter here, and this might be another say 20. So, it is 55 to 60 millimeter at the most. So, diameter will be 120 millimeter, which is less than 5 inch. 120 millimeter will be something like this. So, this is the size of the motor, whereas and thickness is only 14 millimeter. If you multiply with this, it is close to 14 millimeter, but you see this how much volume is required for one rotation. Obviously, this is due to the gearing action inside. So, in this way you can calculate the swept volume. Also you can calculate, you have to obviously you have to make the numerical integration to find out the volume displacement of such machines. So, these are the references. I would say that this paper you will not be able to follow, because this is in this is old as well as this is in German language. I think not even German language, it is something, it is not exactly German language. I think these two people were from Austrian people. If you read this paper, you will have some idea about this fixed axis machine, not orbit motor. Also Kolbarne, he derived such displacement formula for fixed axis, and Thoma, he is I have used this how to phase is changed and other this. So, you can read this book also, but if you would like to know that phase differences and volume change etc., so you can read this paper. Okay, thank you.